Okay, so welcome to the PAC 2015 Escape 25 conference. It's a great pleasure for me to welcome you here in Copenhagen. The conference is organized on behalf of the Cape Working Party, and here in Denmark, it is organized by the Technical University of Denmark. Cape Working Party is part of the EFC, that is the European Federation of Chemical Engineering, and this is the 727th event. And the wonderful Copenhagen organization has helped us with lots of the organizational facilities. And you will see that normally when we are organizing something in Denmark, we also try to order for good weather. And there was some confusion about it, but from today I was told that the weather will improve. In fact, somebody told me that they never saw rain in Denmark until yesterday because every time they came the weather was perfect. So from today onwards I was told that the weather would be improving. And as you see, Copenhagen is a very friendly city, and it is very green. It has a lot of facilities that you would like. We don't want you to go out during the sessions, but afterwards you're most welcome to try the different features. I should start with also the sponsors who gave us funds to help with different aspects of the organization. So thank you for all the sponsors. And you can see on the side of the room, we are also advertising this. And then this opening session, I should also mention that this is a PAC plus Escape. So the PAC Executive Board is also involved, of course, with this organization. And yesterday, Rex Reklitis took over as the chair of the PAC Executive Board. And then Jiri Clemens is the Cape Working Party chair, and Jean-Marc Leland is the EFC Scientific Vice President. So I will ask them and invite them to come and say a few words of welcome, and then I will give you a short overview of the conference. So I'll start with Rex first.
Good morning. I'd like to welcome you to the 12th PSC. As you know, this is a conference series that was started in 1982 in Japan, has been held now 5 times in Asia, 3 times in the Americas, and this is the 4th time it's held in Europe. It's really a pleasure that our colleagues here at the Danish Technical University have taken on the job of organizing this conference, and as you will tell as the conference proceeds, it's really an enormously ambitious conference, the largest of the PSC series that I can recall. And of course, the venue is always better than the one prior to it. It's really great to be here. I think this series covers all of the areas of process systems, from design to control to operations, and all of the numerics and algorithms in between. So I'm sure you'll be really stimulated and excited by the wonderful program that's been put together. So welcome.
So now, Jiri Clemens, please.
Good morning, everybody. I would like to welcome everybody on the behalf of all members of Cape Working Party, and at the same time to thank the organizers. This is the very beginning of the conference, but it looks very well organized, and it is set up to be very successful. This is Escape 25, and 25 is a very nice age when the person is at the beginning of the best period of the life. So I believe that ESCAPE, which by the way started 25 years ago in Denmark, and it's returning for a quarter of the century jubilee back, will live a long time and become more and more matured and more successful. And it depends on all of us. And thank you for coming, thank you for contributing, and putting CAPE research even higher and better. Thank you very much.
And then Jean-Marc Leland.
So good morning, everybody. Today, as acting scientific vice president of FCE, it's a very great pleasure on the behalf of the FCE to see you so numerous in Copenhagen for this joint conference between two famous series events from PSC and ESCAPE. It's the 25th events of ESCAPE, and here it's my duty to remembering you that it was inspired by Professor David Ripin, and it was a continuation of the series, the use of computers in chemical engineering. So what I can say is that I will hope long life to PSC series, long life to ESCAPE series, long life for the joint conference, where I see more and more experts, young scientists, which is very important for our future, and aficionados. So enjoy the meeting. Come back to your sweet home with at least one good ideas or more, one new friends, and enjoyed wonderful Copenhagen. Thank you very much.
So thank you very much, Rex and Jiri and Jean-Marc. For the rest of the time here for this opening session, I will tell you briefly about the organization and some of the programming aspects. So first, some of the scientific highlights of the program. I won't show all the pictures of all the speakers. You have all these in the technical program already. We have 4 plenary sessions with 4 speakers. And then we have, I think, around 15 keynote sessions with 41 keynote presenters. Then around 31 oral sessions. These would be parallel sessions with around 150 presentations. And these are 20-minute presentations, including question answers. And then there are 36 oral highlights plus poster, meaning that each of those poster presenters have 5 minutes to tell about their posters. And then there would be 3 poster sessions, and the poster sessions will have slightly more than 100 papers every day. I should also mention here that the Computers and Chemical Engineering Journal is actually sponsoring the plenary sessions, and the poster sessions are sponsored by Elsevier. The proceedings volume could not include all the papers that are to be presented here because we had an upper limit of 3,000 papers, and then you can already count that 3,000 papers and the number of papers being presented, we cannot include all of them. So we had asked voluntarily for people to remove some of the papers, and they did. We thank those authors very much for allowing other papers to be included. And the proceedings volume has 435 papers. The volume is volume 37 of Computer-Aided Chemical Engineering, and it is, I think all the corresponding authors plus registered participants should have received a link from Elsevier to download the paper, the whole proceedings. If you haven't received the link, please let us know and we will provide you the link. One thing that we did new here is also we created a book of abstracts, because there would be some presenters whose manuscript would not be in the proceedings volume. So the book of abstracts was edited and organized totally by 3 of my PhD students who are the volunteers in this conference, and I think they did a very good job. I said I didn't want to spend any time on it. Please do it as well as you can. And I think you will see that they did a very good job. We also managed to get an ISBN number, which means that you can actually cite those abstracts from the book. And then there will be a special issue of computers and chemical engineering. There will be a larger number of papers than usual, but because of the large number of papers in this conference, it would be invited invitations sent out for authors to submit, but any authors who are interested can contact me and we can discuss about their contribution. So we do not want to exclude anybody, but at the same time, we do not want to receive 200 extended manuscripts, then it would be impossible for us to create this special issue. Some statistics based on the 502 presentations that were registered some time ago. So this number is not the exact number, it has increased. We distributed these in terms of topics, and T1, for example, is the topic where we received the maximum number of papers, and this is on modeling, numerical aspects simulation modeling. Then the second highest, T4, is process and product synthesis and design. Then T2 and T5. T2 is optimization, math programming. T5 is dynamics and control. So the dynamics and control community are very much also involved here. T7 is planning and scheduling. T9.5 is energy systems engineering. T9.6 is environmental engineering. So we have a very wide range of topics, and the papers, the graphs in blue are oral, and the one in brown is posters. The distribution of the papers are, as you can see, out of the 502, 35% oral, 57% poster, 7%, which is 41 speakers, keynote speakers, and 4 plenary speakers. The keynote speakers also has a number of industrial and academic speakers. In terms of participants, again, this is not the final number. Out of the 600 that we had, it's divided into 50 countries, with United Kingdom as the highest, followed by USA. Here I should also mention that NSF from USA provided funds for the US participants, especially all the students and young academia were given discounts or free registrations based on the NSF funds. But we are also very happy to welcome a very large delegation of China and also from all over the world, South America, other Asian countries. From what I can see, the numbers are much higher in terms of the distribution per country compared to the previous conferences. Also, you can see that there are 35% of the participants are students, 54% from academia, faculty members, young researchers, so on, and 11% from industry. 11% sounds quite small, but it's more than 60 participants, so I think it's quite good to have them. In terms of social program, yesterday was the reception that I hope you had a good time at the reception. Tonight, there is a reception at the Copenhagen Town Hall. This is actually given free to us by the city of Copenhagen or the mayor of Copenhagen. Unfortunately, he will not be present to welcome us, but he has sent somebody else to give us a welcome speech. And we convinced the city of Copenhagen to welcome you all. And I told them that more than 400 experts from all over the world on computer-aided process engineering and process systems engineering are coming to Copenhagen. They should show all the good things of Copenhagen and give us a reception. And they agreed with me. So it's a free reception that we managed to get. On Wednesday night is the conference dinner. I hope you will see that it's not the usual conference dinner that you will have in conferences. It is actually an international show with songs, music, dance, cabaret, all kinds of things. It's a 3-hour show, including food, and good quality 3-course dinner plus the show. And so the tickets are all given to you. It's part of your registration. If any of you need some extra tickets, please contact the secretary office and we'll try to give you. But we have a maximum of 600. The whole place is reserved only for us. And at the end of the show at 11, they will create a discotheque for us if we want to continue, especially for the young people. So finally, I would like to thank plenary speakers for accepting the invitation and coming, all the keynote speakers, all the authors of the contributed papers. It is also very important that non-author participants are there, and we have a large number of that. So thank you for also coming to listen to the papers. Members of the International Scientific Committee, their help was very important for the review of 500 plus papers. Members of the organizing committee, that's a large committee, including my faculty colleagues, plus our PhD students and postdocs, plus a large number of volunteers who had been working already from 8 o'clock in the morning yesterday, preparing the bags and the name tags and all these things. So thank you all. And then I would like to give a special thanks to these people because they have been doing much more than everybody else. You probably have received quite a lot of emails from Eva Mikkelsen and Stefano with respect to all kinds of organizational matter. Rebecca, Mariona, and Thomas, they are the ones who made the Book of Abstracts and all the signage and lots of other things. Syed, Amata, and Stefano made all the organizational matters. So they all worked as a team and helped us do this without having to hire any commercial conference organizers. So everything was done locally by us. So a special thanks to them. With that, I will finish now. I just hope that and wish you all a very good time here. We have a very good and interesting technical program, and we hope that the organization of the conference and the conference venue will work for us to give you a memorable time. But at the same time, I hope when we go out, the social programs are also interesting and useful. Thank you very much. And now we will start with the plenary.
Good morning. Good morning, everybody. I just want also to extend a very warm welcome to all of you to coming to this joint PSC and ESCAPE event. A particular note of thanks to Professor Rafik Ghani and his team for actually making this successful event. First of all, from participants, it's great to see so many of you here. This is a vote of confidence for the process systems engineering and the CAPE communities. And I think the only way is way up. So a round of applause for Rafik and his team, first of all. I think you will also agree with me that there is no better kickoff for a conference like this, not a better representative of the values and of the dimensions and parameters that define the process systems engineering spectrum and the CAPE community than our speaker who is going to give the inaugural plenary lecture. So a very warm welcome to Professor Ignacio Grossman. Ignacio is the R.R. Dean, University Professor of Chemical Engineering at Carnegie Mellon, where he was, as many of you know, also a very successful head of the department there for quite a long time, and now he heads the Advanced Center there for process decision making. Ignacio is a member of the National Academy of Engineering in the US. He has received numerous awards, including the Computing Award, the William Walker Award, the Warren Lewis Award, and the Research Excellence in Sustainable Engineering. He is a very prolific author with extensive citation, named in the 2014 Thomson Reuters as one of the most highly cited people, one of the very few in the chemical engineering profession. And he has a very impressive academic tree. Recently, we celebrated his 65th anniversary with over 200 plus academics around the world in eminent positions. He was also named one of the 100 most influential chemical engineers of the modern era, so it gives me a great pleasure to introduce Professor Ignacio Grossman, who is going to provide us a map of recent advances in mathematical programming techniques for optimization under uncertainty. Ignacio.
Thank you. Right. Well, first of all, thank you very much, Stratos, for a very kind introduction. And I'd really like to thank also very much the organizing committee, and in particular, Professor Rafik Ghani, for inviting me to give this plenary lecture. Now, today what I'd like to do is to share with you some of the recent work that we've done in the area of mathematical programming-based approaches to optimization under uncertainty. And here, as you can see, we have really four co-authors. These are Rob Appa, Bruno Calfa, Pablo Garcia-Herreros, and Xi Zhang. And it's really through them that I'll be based the presentation, because it just so happens that the four of them are actually doing their PhD in areas related to optimization under uncertainty. I think if we look at the motivation for this area, it's of course very clear that we deal with problems in process systems engineering, whether they're synthesis, design, scheduling, control. There's always, of course, a great deal of uncertainty, especially in terms of the parameters that, we use in these type of models. So if we look at design synthesis, we have, for example, uncertainty in the quality of the feedstocks. We have kinetic constants, transfer coefficients that are uncertain. If you look at supply chain planning type of problems, things like product demands, prices, yields, again, are all usually highly uncertain. So the basic questions that we face when we want to approach this problem is really of three types. The first one is, how do we actually model these problems? Because it's not easy to always articulate what we really want to accomplish in a problem of under uncertainty. The second one is that, unfortunately, very often the computational time required is not one, but sometimes several times orders of magnitude longer than a deterministic model. So how do we effectively solve these models? And the third one is the quality of the input data. The question is, can we make use of historical data and forecasts to improve the accuracy of these type of models? Now, I should start out by saying that actually the area of optimization under uncertainty is not really new in process systems engineering. If you look throughout the history, we'll see that during the 70s there were a number of interesting papers published in the area of optimal design under uncertainty, and subsequently in the late 90s, early 2000, there was the shift towards planning under uncertainty. Then the other area that received attention is robust optimization. I'd like to point out the fact that there was this very interesting paper by Rex Recladis in 75 that was essentially, I would say, 34 years ahead of his time. And then the other approach that has also received attention is chance constraint, although it's been somewhat smaller. And here the lead has been taken by the group of Professor Watson at the Technical University at Berlin. So when we look at these type of different works that have happened, again, a big issue is, again, what approach are we going to use to anticipate uncertainty? And here, that's where different models arise. For example, if we assume that we have a deterministic uncertainty set, then usually the major concern in robust optimization is to ensure feasibility for that uncertainty set. And that's shown here in the figure, where basically the idea, you have the uncertainty set given by the set U. You want to make sure that it is inscribed within the feasible region. Now, but often, of course, we assume that the uncertainties are described by some type of probability distribution function. And here the natural framework is stochastic programming. In stochastic programming, usually the major objective is to optimize the expected value, which is sort of the average value. But another very important concept in stochastic programming is the idea of recourse, meaning that actually you have two types of decisions, sort of the here and now, which is the stage one. You need to make a decision without knowing how the uncertainty will be revealed. And then the other one is a recourse decision, which is those decisions where you can wait and see until the uncertainty actually realizes. The other thing that also makes the problem complicated, you can also add, for example, some risk measures in order to try to take care especially of the tails of the distribution. And the other approach related to distribution function is the so-called chance constraint optimization. In many ways, it's actually also very much related to robust optimization, except that here we work with the probability of meeting the constraints, which in general is in fact a much harder problem because you need to integrate the distribution over the feasible region. Now, if we look at all the work that has taken place, obviously there's been important advances, but one of the issues is actually the impact at the level of industrial practice has been somewhat limited. It has been somewhat limited because, again, there are some important issues and problems. And I would say, if I had to point out two major reasons, the following. First of all, the problem of optimization under uncertainty, we could say, is kind of an ill-defined problem. Ill-defined in the sense it's not simply a unique formulation like the one that I've indicated here. So that's one major problem. But the other problem is, again, the scaling. Scaling, when you increase the problem size, computational expense is a major challenge. So what I'd like to share with you here are some of the challenges and barriers that we, will try to overcome in this area. And the first one is the question, how can we make robust optimization to be, if we wish, less conservative? Because that's one of the major criticisms of robust optimization. The second one is, yes, we want to apply two-stage, maybe multi-stage stochastic programming. Can we do this effectively from a computational standpoint? The third major question or challenge is the question of dealing not only with the usual exogenous uncertainties, but also with endogenous uncertainties, which, as we're going to see, greatly complicate the formulation of these problems. And lastly, again, there's the issue of improving the quality of the information that we have using historical data and forecasts in our models. Now, I should mention that actually in this presentation, we will be restricting ourselves to linear models, mainly linear programming and mixed interlinear programming. Now, of course, the extension to nonlinear usually follows, but it's of course also a major step that I'd like to recognize from the very beginning. So if we start with the area of robust optimization, mathematically in its most general form, it has the following form where you want to minimize the worst case for the objective, so you maximize with respect to the parameters u, and subject to the constraint that you want to satisfy the constraint g of x for every point u in the given uncertainty set. Now usually this problem can be reformulating by placing the objective function as a constraint, so in that way you're really dealing with a problem with an infinite set of constraints. So for that reason, conceptually, at least this problem corresponds to a semi-infinite programming problem. In this problem, if you look at the literature, Bental, Bertimus, two major references here, usually the starting point is a linear programming problem as the one that I've indicated here. Although I should mention the extension to the mixed integer case is usually in that sense fairly straightforward. And here, the way the problem is usually addressed is to realize that the uncertainty set could be, taken different forms, could be simple lower upper bounds like this were indicated here, or could be some type of one norm, or could be a more complex description of the uncertainty set. Now, if you look in the process systems engineering literature, what's been done in the area of robust optimization, well, we see a lot of the applications have taken place actually in the area of scheduling. And that actually makes perfect sense. Why? Because when you have short term, often there's actually not much provision for recourse decisions. In that sense, it's quite appropriate. But it's also been applied, for example, to supply chain, and very recently also in the area of process synthesis. Now, if you look then again at the formulation of robust optimization, so again, you could think of it as being as optimizing for the worst case, and that means that basically again we're contending with this linear problem that I presented before, where I think one of the conceptual issues here is that the variables x over which we're optimizing, there's no distinction between the here and now and the wait and see. In effect, we can say that all the variables are treated like here now, so we make just one decision on them, and there's no provision for any recourse. And here again, it turns out even in the linear cases may not be such a simple problem. It all depends on how we have the description of the uncertainty set. If it's a simple polyhedral, it's usually fairly straightforward. If it becomes nonlinear ellipsoidal, that could start to become a little bit more complicated. But the point is that so far, if you look at most of the work on robust optimization, it does not account for recourse. And here I would say the nice and important development that has taken place is in 2004, seminal paper by Bental in the journal Mathematical Programming, where the idea here is that we're now going to make a distinction between the x1 and the x2 variables. So x1 is as before the stage 1 variables, and x2 are variables that are going to react according to the realization of the uncertainty. And the idea then here is that we're going to apply what is called sort of the robust counterpart, because robust counterpart means essentially we're going to apply duality theory on each of the constraints and transform the problem into a single optimization problem. And as you can see here, the key point is the variable x2 is now going to take reactive actions according to the realization of the uncertainty. Now, how can you reformulate such a problem? Well, the idea is that if you have a description that is, say, polyhedral or maybe conic in nature, the problem is tractable in the sense it's solvable in polynomial time. And here what we're doing, we're representing the matrices A1 and A2 as ones where you take a nominal point and you have the contribution of the deviations that are affecting then directly the uncertainty, uncertain parameters. And the idea here, and this is the key point here is to postulate, and this is the linear decision rule, we're going to postulate that the recourse variable is a linear function of the uncertain parameters. So the coefficients to be determined here are the Q0s and the QL that we want to determine in order to anticipate that recourse action. And how do we do this? Well, again, we'll assume linearly. This is called the affinely adjustable robust counterpart. It turns out that if you assume that for the matrix A2, okay, we do not have any deviations, so all the uncertainties in matrix A1, this problem does become tractable. And essentially what you can do is you can then formulate this problem and apply very much the same approach that we use for the case where you have only stage 1 variables. And this is illustrated here in the next slide, where essentially what we're doing, we take the formulation I presented in the previous slide, and then for each constraint, you maximize it, applying a dual formulation, and this is basically the formulation that you end up with. So basically the concept is we're converting an LP with uncertainty into another linear programming that of course is extended in size, but it's still, reasonable in terms of the computation. And I should also mention that this idea can actually also be extended for the case of multistage optimization. Now, the reason we got also especially interested in this problem is to think at what is the geometric interpretation, when we do anticipate recourse. So here let's assume that I have 3 variables, design variable D, that's a typical here and now, Z is a recourse, that typically would be a wait and see, and U is the uncertain parameters. So let's assume I have this simple optimization model. I want to minimize the design variable D, and I have a set of constraints that involve the uncertain parameters, the design variables, and also the control variable Z. Now, in the case where we do not make a distinction between D and Z, and we solve the problem applying the robust counterpart, this is the optimal solution. D is equal to 2 and Z is equal to 2. And if you want to see geometrically what this means, geometrically if I plot here uncertain parameter U versus the control variable Z, for these parameters this is what basically bounds the feasible region. In fact, if you look at the uncertainty set, which in this case is defined between the values of 1 and 2, you can see that with the solution Z equals 2, we exactly achieve feasibility within those constraints. So we've opened up the constraints so that with a single choice of the value of Z, we can then meet the constraints over that uncertainty set. Now, what happens when we use the recourse idea, the fine adjustable recourse? So here we're going to postulate that the control variable Z is the linear function of U. Then again, we apply the idea of the duality theory. And then if we solve the problem, we find that D is equal to 1. In fact, this is now the feasible region. So we have now a feasible region that is in fact much tighter. And not only that, but what's also interesting, if you plot the recourse variable Z here that we have at this point, you can see, you can see that actually corresponds to the red line. I think I lost the light here. I do have a backup here, just in case. Let me see. Lost here the lights. Yeah. Okay, yeah. So the red line that you see here actually corresponds to this control function, and essentially what it's doing is achieving feasibility over set U. So in other words, we're achieving less of an over-design because we're being less conservative. The other interesting point, as you mentioned here, the ideas of linear decision rules are in fact also very much related to the work on flexibility analysis, where I'd just like to point out flexibility analysis in some sense is actually more general than what we have here. Now, we've applied this to a problem that is related to a project that we've had with Praxair. It deals with the integration of an air separation unit with cryogenic energy storage. And the idea here is basically the following. So what we have is an air separation unit where we're producing oxygen and nitrogen, both in the form of gas and in the form of liquid. I should also mention that, in fact, this presentation will be given tomorrow by my student Shi Sang in the session on energy systems design and scheduling. So what's interesting in this problem here is the idea that we're going to add as a possibility to store energy in the form of cryogenics. And the way we do this here, as you can see, essentially some of the liquid product, which is at high pressure, we're going to store here. And whenever we want to have this available, we heat it up and then we expand it through a turbine and generate electricity. Electricity could then be used for internal use. It could be used for selling into the grid to the electric energy market. But the interesting part here is also to consider what is called the reserve demand. This turns out to be the idea of providing power at some given need whenever the need arises. And the big question here is there's a lot of uncertainty as to what that reserve is going to be. That turns out to be, from an economic point of view, an important source of the economics. So this is the main uncertainty that we're anticipating here. So here, instead of taking a traditional robust optimization approach, what we're doing, we're saying, well, we're going to make a distinction between the first stage and recourse decisions. First stage, I need to design the base plant operation and the reserve capacity. Reserve capacity is a major variable I'd like to determine to know how much power I can supply on a need basis. And the recourse decision is a liquid product that is being produced. It turns out if you formulate the corresponding optimization problem, as we've seen in the previous slide, it's about 50,000 variables and constraints, 2,500 binary variables. Takes about 10 minutes to solve this to 1% optimality gap. And this is the result that we're obtaining here. This is the schedule for the operation, where here essentially you can see, first of all, at the lower end, here we have the pricing of electricity that is changing as a function of time over 1 week. Then here the green bars represent how much liquid is flowing into the cryogenic energy storage. Then what we're doing here, what the model is actually predicting, is in blue the power that is being converted for internal use. So that's power that we're saving instead of having to buy it from the grid. And then here in the brown area here, this is actually the one that we're exporting. But the important result here is the one of the reserve capacity. That's the one that actually the optimization is determining. And again, the important thing is we're including flexibility by the fact that we are allowing for the recourse by adjusting the production of the liquid. Finally, what I'm showing here, this would be the profile of the liquid that is actually being stored in the tank. So again, you can see this fairly complex problem, but it's one where instead of just being very conservative, we do allow for the possibility for the recourse. So let me now move to the next area, which is stochastic programming, which, as you know, is a framework in which we have uncertainty, but based on scenarios. And the idea here, typically, you have a sequence of time points, because you consider often multiple stages of decision. And the distribution function is usually represented as a discrete probability distribution function. Reason being that if you do, continuous distributions, you're confronted with multiple integrals. So that's a major approach that's been taken here. So essentially here we have then in the discretized distribution, which you can represent in the form of a scenario tree. These are sort of the main ingredients of stochastic programming. And if you look at the mathematical formulation that's shown here, basically what we have, we minimize in this case with respect to the stage 1 variables x1, and you take the expectation, for example, with respect to the recourse variables x2. This would be the average cost of operation. But we're showing here for multiple stages. This is an embedded expectation. The simplest case to think about is, again, just the one of the two-stage programming, where you have the stage 1 variables x1, x2 are the ones that are reacting according to the realization of u. But this then gives us sort of the general framework for the formulation to this problem. And here again, if we look in the process systems engineering literature, what has been done in this area, initially a lot of it was actually applied for design and synthesis problems. It has also been applied quite extensively to supply chain type of problems, because it makes sense. These are longer term type of problems. And there's also been, for example, some applications to scheduling, and there's also a rich literature in terms of how to improve the methodology for solving these problems. So here what I'd like to discuss is the issue that when we solve these problems, we really need to resort to some decomposition, because these problems can become quite large in terms of the number of scenarios. And the two major schemes that we have are, on the one hand, Bender's decomposition, which is sort of the natural way of doing the decomposition, because here you have complicating variables that are typically stage 1 variables. And once you fix them, each one of these blocks will correspond to different scenarios. In each one of these scenarios, you can then solve essentially in parallel. So Bender's decomposition, I think it's fair to say, is sort of the major framework for solving especially two-stage stochastic programming problems. But the other decomposition scheme is the Lagrangian decomposition scheme. So here the basic idea is that we have complicating constraints. These arise normally by reformulating the stage 1 variables, assigning them to each period, and writing some equality constraints. And that turns out to be especially useful for multi-stage stochastic programming. So Bender's is mostly two-stage. Multi-stage is usually with Lagrangian decomposition. So the specific problem I wanted to address here, this is the joint work also with Dow, is the issue of how to design a supply chain that is going to be subjected to disruptions. Disruptions is the uncertainty here. This could arise because of things like earthquakes, fires, strikes, or major events that will prevent that distribution center from being available. So as you can see in the diagram here, we assume we're given a given supply plant that's going to send the material to these potential distribution centers that in turn are going to feed the product to these various markets or customers. So the design problem here is then essentially to determine the distribution centers that should be selected, the candidate locations. The other very important parameter is capacity. How much material are we going to have in storage? And then how are we going to allocate the distribution centers to the market? So again, sort of a typical classical type of supply chain optimization problem. And here, this is again a typical sort of a two-stage stochastic programming problem in the sense that you can see here, stage one decisions are related to the distribution center, 0, 1 variable to decide whether or not to install it, and C is the capacity. And the second stage decisions is the variable Y that tells me what percentage of a distribution center gets allocated to a given market, and that can change for each one of the scenarios. Now, the mathematical formulation of the problem is given here. Don't want to describe it in all detail, but just to give you an idea, the objective function is to minimize costs. We have investment, we have the transportation of the distribution and customers, the storage, and then there's also penalties. Penalties for not meeting the constraints. Constraints are storage capacity, demand satisfaction, and the last constraint is the one that will tell us how much is really available, and it depends on this matrix T that will indicate whether or not there is a given disruption. So that's sort of the nature of the model. It's a mixed integer linear programming problem. And just to illustrate the nature of this model, let me give you first a very simple example. We have, as you can see, one plant. We have 3 potential locations for distribution centers with these probabilities of disruptions and 6 markets. So in this case, if you formulate the problem first in a deterministic fashion, assuming there's no disruption that will take place, the optimal solution, as you can see here, is to have these 2 distribution centers. This one is actually not needed. The first one is assigned to the first 3 markets, the second one to the other 3 markets. And this is the investment cost as associated, $279,000. Now, what happens when you do anticipate disruptions? There's actually 8 different scenarios here. So what happens, you can see now in this case, the structure changes. We are adding a new distribution centers, and we're actually also increasing the capacity of storage in these centers. Now, obviously, that will increase the investment, as you can see here, but when you account for the penalty for not meeting the constraints, you can see that in terms of total cost, this is $600,000 versus $1 million if we do not anticipate the effect of the disruption. So that's sort of the nature of this type of problem, to try to predict the system, for these unusual events. Now, what is the problem when you want to, apply it to large-scale problems? Well, first of all, the number of scenarios increases exponentially. That's the first problem. Secondly, from a mixed integer programming point of view, the relaxation is rather weak, and that's bad news for Bender's decomposition. It means it might take a large number of iterations. And then the other issue that we have here is potentially a very large number of scenarios and with very different magnitude. So what we're going to do here to approach this problem, we'll see how we can, for example, select a subset of the scenarios, how we can actually improve the relaxation, and how we can actually exploit the structure of the probabilities. So let me consider first the issue of tightening the formulation. So what we're going to do here, we're going to add an extra redundant constraint to our problem that has a very nice feature that by adding that constraint, we can actually prove that this set of constraints corresponds now to the convex hull. So that means that that set of constraints has integer points for the extreme points, which is a good thing for mixed integer programming. And this you can see clearly here. This is the MLP formulation for a given problem with the 600,000 for the expected cost. You can see the traditional LP relaxation has a lower bound of 420 for the cost, which is quite below. If we apply this reformulation, the lower bound increases from 420 to 589. So clearly, you can see we have a great improvement by doing this tightening of the relaxation. Now, next, what we're going to do is reduction of scenarios. We're going to see a number of real scenarios could be absolutely absolutely huge. So how can we reduce them? Well, there's basically three different approaches you can use it. One is sampling. For example, the sample average approximation is one such technique. The other one is to use scenario tree reduction, like the one by Remes and by Chris Flores. It's a deterministic way of reducing the size of a scenario tree. But in this case, what we're going to do, we're going to exploit the fact that we know that there is an ordering of probabilities. For example, probability of having no disruption is always going to be greater than when we have up to 1. This will always be greater than we have up to 2. And that will give us actually a way of selecting a subset of the scenarios. What we're going to exploit then also here, taking advantage of that property, we're going to be able to take only a subset of the scenarios and develop lower and upper bounds. The way we obtain the upper bounds here is simply with the idea of saying, well, those scenarios that are not being considered or are being neglected, we're going to be able, if we find a feasible solution, feasible assignment, we assign them a cost. If we cannot find a feasible solution, you assign to them a penalty. And that will then give you sort of a conditional probability. And this is sort of captured in this diagram where you can think of it as this is the total number of scenarios. The area in blue would be those scenarios that we're neglecting. That in general is going to be the largest amount of the scenarios. The area in gray area here, that's the one where we do explicitly consider the scenarios. And the area in dash is the one where we're going to do some type of sampling to infer what's happening with the rest of the scenarios that have not been taken into account. So that's sort of the basic idea here. Now, we apply then this type of approach also with Benders decomposition. Only point I want to make here, this is not a straightforward application. We need to do things like not only selecting the scenarios, but also special cuts, Pareto cuts, multi-cuts, and also exploit, for example, parallel computation. Now, this is the industrial example that that Pablo, my student, actually confronted, that had 29 distribution centers with disruption between 0.5 and 1.5%. 110 customers in the market for 61 different products, 61 commodities. Now, what's interesting here is to see how the problem size increases as you start considering number of disruptions. So, for example, if there's no disruptions, you're capturing only 59% of the cases. You have about 3,000 constraints. If you take up to one disruption, you take 30 scenarios, but now you can see number of constraints goes from 3,000 to 60,000, although now you cover 90%. If you go to 3 scenarios, we need 4,000 scenarios to capture that with a very high probability, but number of constraints is 8 million. 8 million constraints and 33 million variables. It's an absolutely huge problem. You can see that this problem absolutely explodes. So the question is, how do we actually solve such a problem? And by the way, so here, keep in mind that the absolute worst case, if you were to take all possible cases of disruptions, we're talking of something like 500 million different scenarios. There's absolutely no way that you can formulate a problem and explicitly account for those different scenarios. So again, what we've done then here is the following. So what we're doing is to say, well, first look at the case where there's only that one single scenario. You can see it solves in basically no time, but the problem is that the quality of the bounds here is not very good. We have a gap between 57 and 48, so that's the most that we can infer. If we go to the next step, and in this case, we, for example, consider up to one simultaneous one disruption, we have, again, high probability, 59 to 95%. We close the gap. There's still a gap between 56 and 52, but notice the computer time now goes from less than a minute to over 1 hour. Furthermore, if you go to the next step and you say, well, let's take, say, 436 scenarios, okay, which is larger, we now have a much closer gap between the lower and upper bound. For all practical purposes, we've achieved the solution. But if you look at the computer time, look at how long it's taken, 1,700 minutes. That's almost 30 hours of computer time. Now, you might say, well, isn't not a better way to solve this problem? Well, if you look at some of the details here, you can actually see that, for example, we're converging in only 6 iterations of Benders decomposition. So that would be, I would say, almost the optimal performance. And the other thing that we can also observe, we have, potentially here 3 million continuous variables, more than 4 million constraints. There's no way we can solve this problem, even compile it, if you wish, simultaneously. So although 30 hours is, of course, a long computational time, realistically, this is basically what it takes to solve a problem of this type of complexity. So let me now move to the third part of the talk that deals with the different types of uncertainties. It turns out if you look at the literature, essentially all of it deals with what is called exogenous uncertainties. Exogenous uncertainties mean that these are uncertainties where our decisions do not affect at all, if we wish, the distribution or their realization. Example could be price of crude oil. It doesn't matter whether I decide to install or not the refinery, that's going to be the price of the crude oil. But there are other uncertainties which are called endogenous uncertainties, where these uncertainties are affected by the decision. And in particular, they're affected, for example, by the timing when we make those decisions. And an example here is the size of a reservoir. If I go and I drill a well at some point in time, then that uncertainty becomes relevant. But if I make a decision not to drill, for example, the well, that uncertainty is not even realized. So it's a conditional to making decisions. Same thing is, for example, in the case of clinical trials, where if you perform the test of a drug, then that uncertainty will be realized about the efficacy. But if you don't happen to the testing, that will simply not even be realized. Now, so here again, if you look at the work that has been done, this is very, very small amount of work in terms of the literature. Here, I'd like to acknowledge the pioneering work by Jonspraten. This is a PhD thesis in Norway, where for the first time this was identified as the two major types of uncertainties. And if you look at what's been done in the literature, well, a good part of it has been done by our group at Carnegie Mellon related to oil and gas field process networks. Christos Maravellas has also done some nice work for pharmaceutical clinical trial planning. And Natasha Boland at Australia applied it to open mining problems. But it's very scarce, the literature. What's even scarcer if you look at the problems that are related to both exogenous and endogenous at the same time. Right now, to my knowledge, there are only two papers that have been published on that problem. So the area, I would say, is wide open. This clearly deserves attention. Now, why there is that complexity? Well, let me try to walk you through, how we construct scenario trees and how scenario trees for endogenous are actually rather complex. So in the case of exogenous uncertainty, what you have here at time t equals 0, you make a decision, then the uncertainty gets realized with the two nodes that you can see here. Then at the end of that time period, you take a recourse action. You're going to take some corrective action here. Then the next thing that you do, you make a decision at t equals 1. Then the uncertainty gets revealed, and then you open these two nodes. So essentially here, what you can see, and again, at the end, we take again a recourse action. The main point or the main message is when you have exogenous uncertainties, the structure of the tree is fixed. In fact, a nice representation of that was developed by Rusinski with the idea of using so-called non-anticipativity constraints. Idea here, instead of using the tree representation, if you walk through this first path, that's scenario 1 that you have here, the second path, scenario 2 that is here, and so forth. So what you're doing here essentially with the bars, these represent constraints that are basically equating the states. So for example here, the y1 decisions that I make at the root node at this node are going to be the same as I have them here. So I write this as an equality constraint. So non-anticipative constraint just simply means we're adding equality constraints to merge, so to speak, the nodes, recognizing that they have basically the same piece of information. And that can be done rather nicely again with this type of representation when you have the exogenous uncertainty. Now, what happens when you have endogenous uncertainty? Well, what happens is, for example, the following. So let's assume I decide to invest in a given source 1, then the uncertainty will be revealed for theta 1, could be low or could be high. But then if I don't do any further investment, that's the size of a tree. That's it. It has not the shape as the one that we had before. So here clearly again, if you relate it to the Rusinski type of representation, the graph representation, what we're seeing here, the bars correspond to the non-anticipativity constraint that are saying, well, this node is really the merger of these two nodes in scenarios 1 and 2. Now, what happens again if I take different decisions? If I first invest in source 2, then this is low, this is high. In this case, let's say I do decide to invest in source 1, and this turned out to be a good alternative. And you can see what's happening here. The tree depends on what decisions I make. And this is a great complication that we have with endogenous uncertainty. Now, the question is, how do we treat this? Well, in order to be able to address this problem, obviously what I need to do is to develop sort of the equivalent of a superstructure for the endogenous parameters. So here, for each one of the scenarios, the dashed lines correspond to potential lengths that will enforce these non-anticipativity constraints. And, well, how do we model this? Well, the way we model this essentially is with a disjunction. We just simply say, if this Boolean variable is true, we're going to equate the variables, so we're going to enforce, for example, these bars. If it's false, we're just simply going to ignore it. And again, this is illustrated here in this figure. This one is always applied here at the root node, but for example, the intermediate nodes, it will depend whether or not that Boolean variable is true, that we're going to equate the variables in order to merge the nodes, okay? So in that sense, we have sort of, in principle, a conceptual way of representing the variable scenario trees. Now, then the question is again, how do you formulate mathematically such a problem? Well, first what we do, we take the Cartesian product for the endogenous uncertainties. We take the Cartesian product for the exogenous. That gives us all possible options. And then what we really need to do is to construct like a composite tree where we're merging both the endogenous with the exogenous uncertainties. That's given here by taking the product of the endogenous with the exogenous. And this would be, if you wish, the graphical representation. What this means here is really the following. At the high level, we have the endogenous uncertainties, where, for example, here I have two. This is the low-low, the low-high, high-low, and high-high. Those are the four different outcomes I can have for the endogenous uncertainties. And then for each of them, I have a subtree for the exogenous parameters. So I'm really like replicating the exogenous for each possible realization of the endogenous parameters. Now, this problem we can formulate mathematically as follows. So if you do the stochastic programming problem, well, this is the expected cost subject to the constraints for each time and for each scenario. So this part is fairly straightforward. The part is not so straightforward as the part that follows. All the extra equations I'm writing here is simply for the non-anticipativity constraints. Some of them, of course, are fixed, like for the first period, but here we have, for example, conditional constraints that are needed, for the corresponding binary or Boolean variables. So the main point here, or main observation, is because of the fact that here I need three indices for every time and every pair of scenarios, the number of constraints just explodes. And that's basically the computational challenge. So what can we do about this? Well, what we can do about here is essentially the following. We can eliminate actually some redundant non-anticipativity constraints, exploiting things like properties of symmetry, properties of adjacency, of transitivity, and of grouping. So exploiting basically what we're doing here, for example, in the case of symmetry, recognizing if I do scenario 1 and 2, I don't need to do scenario 2 and 1 because they're basically essentially equivalent. The big problem is that even with these eliminations, we're still going to be facing a large-scale optimization problem. So what can we do about this? Well, essentially we developed here two solution methods. One is a heuristic solution method, sequential scenario decomposition, which uses sort of the hierarchy of first concentrating on endogenous, and you fix those decisions, and then you concentrate on the exogenous. And we complement that with Lagrangian decomposition. Now this we have applied, we've had a collaboration for a number of years with ExxonMobil, where actually this idea of endogenous uncertainties originated. And what we have here, we're considering three different petroleum fields, 1, 2, and 3. The amount of oil in fields 2 and 3 is known. Here we have 560 million barrels of crude that we can extract. Here's 500 million barrels. In the case of field 1, it's unknown. So basically it's an endogenous uncertainty because it'll depend whether or not we're going to actually end up exploiting that field. The exogenous uncertainty is the price of oil and gas. That's basically the exogenous uncertainty. And what we're considering here is the potential of installing these floating production platforms that are going to be then assigned to the different fields for the drilling of the oil. Okay. Here also I should mention the nonlinear performance of the reservoir. We model with piecewise linear approximation to keep the problem as an MILP. Now, in this case, so what we're doing in terms of the problem, we take 5-year horizon. Investment decisions, again, which one of these FPSOs we're going to install. We also need to worry about how we're going to connect them to which field and what is the schedule of the drilling. That's basically the first stage decision. The recourse here is to keep the level of the production. So here, if you look at the problem, even in the simplest case where I take, say, a good value and a bad value for the size of field 1, then I have 2 endogenous combinations. In the case of price, again, if I take high and low as 2 possibilities over the 5 time periods, I get 32. So I get a total of 64 scenarios. 64 at first sight doesn't seem to be that large. But nevertheless, we'll see even that can do, quite a large problem in itself. So this is the optimal solution that we actually obtained. You can see expected net present value is $7.1 billion. And here, essentially, these 2 FPSOs are the ones that are being selected. This one is being assigned to field 3, this one to both field 1 and 2. And what's interesting here, when you look at the optimal solution, there is a lead time of 4 years once you make the decision. So it comes on stream on year 4. In year 4, we're exploiting fields 2 and 3, the ones for which we do have the information. There is no uncertainty. And then what makes sense here is to do the exploitation for field number 3 a year later, which is the uncertain field. So that's sort of qualitatively what the optimization model is doing, which actually seems to make perfect sense. Now, what about the computation? Well, you can see here, if you attempt a full space problem, essentially what happens, the main issue here is the fact that we have of the order of 7,001 variables, 300,000 constraints. Eventually, we run out of memory because the relaxation is not very good. Then for the reduced model, the good thing, we can reduce the number of constraints from 300,000 to 124. We get a 62% reduction. So that's significant. But you can see computational time is still of the order of 10 hours. Now, in this case, what proved to be actually quite remarkable is that with the use of the heuristic, we generate the solution, 7.1. With Lagrangian decomposition, we compute an upper bound to that solution. Now, that's only within a gap of 0.2%. But the important thing you can see here, total computational time is actually only less than 1 minute of computation. In less than 1 minute compared to something that could have actually taken 10 hours. So this is sort of one situation where, fortunately, we're achieving a very large reduction. So with this, let me just go into the last part of the talk and consider the issue of use of historical data. What is the issue here? The issue, we're putting together these models. I need to specify probabilities. I need to specify what the outcomes are. What numbers do I use? Well, the logical thing to do is to think, well, obviously we'd like to make use of historical data. And here again, this has been a project jointly with Dow Chemical for data-driven modeling of uncertainty, trying to make use of historical information to incorporate that in our models. This could be done. We initially did this for 2-stage stochastic programming. So again, here, the issue, the uncertainty C, which is exogenous in this case, how do you specify it? Where does it come from? Well, what values are we going to provide for that? So essentially here, the question that we wanted to address is, can we systematically generate scenario trees using historical information? And conceptually, we can see at the end, it's basically sort of like a parameter estimation type of problem where we compute the outcomes and the probabilities. So specifically, this would be the scenario tree with 4 different outcomes. So what I'd like to determine here in terms of the optimization are the probabilities. What probabilities should I assign to each one of those branches? And the outcomes. What are, for example, the amounts of oil that I have in the reservoir? What are the demands? Those are the numbers I would like to generate from historical data. Now, it turns out this problem has been addressed before in the literature by Hoyland and Wallace. Essentially, the idea, what they did, they matched essentially the data with moments, higher moments going from the mean to the variance, kurtosis, and so forth. And in that way, then they obtained values of probability and of the outcomes. The big problem that there is conceptually with our approach is you can very easily run into under-specification. So in other words, it means if the problem is small, you have enough data, to consume the degrees of freedom. But if you have, for example, more of these branches, or even if worse, if you do multi-stage, then you run into under-specification, and then the problem does not have a unique solution. So here, to alleviate this type of problem, what we did, we considered as additional information that we can feed into the model the use of an empirical cumulative distribution. This would come from historical data. You can actually infer such empirical distribution function. And then the idea is simply to say, well, take, for example, the first outcome has a probability, for example, of P1. The second one is probabilities P1 and P2 and so forth. So that then allows us to add additional constraints to the parameter estimation problem. And this we can see then in the next slide. This is the original formulation by Holland and Wallace. So the objective function, we're minimizing weighted error between the information in the tree, the moments, and the covariance. That's essentially what you have in this term, the moments and the covariance. Then you have the constraint that the sum of probabilities be equal to 1. The next set of constraints, you calculate the moments and higher order moments, and then you compute the variances, and of course you specify the variables. So this is a nonlinear programming that Holland and Wallace basically had proposed. And the only thing that we did here was to say, well, we do have additional information we can generate with the cumulative distribution as given by this set of additional linear constraints, and that will then give us sort of a coherent way of estimating the probabilities and the outcomes. And this procedure can actually be extended to multi-stage stochastic programming, as I'm showing here. And let me just illustrate this with a very small example problem. This is a process network. I have raw material A, where I'm using process 1 to produce an intermediate B. And that intermediate B could go to process 2 to produce product C, and it can also go to process 3 to produce product C. So it's simple process network. What we have here, two cases. One, let's say the yield of process 1 is uncertain. So in other words, there's variation. We don't know exactly the value. The second case I'm going to consider is uncertainty in the demands of the two major products, C and D. So let's take the first case. So let's assume that from plant data, I have an histogram, and this is the information that I do have available. So how to make use of that information? Well, we basically feed it into part of the model. We can extract the empirical cumulative distribution function. And what we get here is the following. What I'm showing here in the left, this would be what I would call sort of the heuristic or naive type of approach, where I say, well, let's say the most likely value is 0.5 yield with 40%, then the next two are 20%, and then 10%, so I have a nice symmetric distribution. But obviously, this doesn't have to do very much with the actual data. So if you look at the nonlinear programming problem, where we are actually predicting these probabilities and the corresponding outcomes, this would be the distribution that we're predicting. And of course, this looks a lot closer to the histogram. And again, not surprisingly, we also get the result that with the heuristic tree, that is sort of the intuitive one, we're predicting a profit that is actually less than the one of the where we're doing the matching, just simply because we have now a more accurate representation of our problem. Now, what happens in the case where there is uncertainty in the pricing? So here we take time series information. We're applying the ARIMA here with non-zero mean as a stochastic process to do the estimation. And here again, this would be the heuristic approach. You would postulate here this tree with these different outcomes for the demands as a function of time. Now, if you apply the procedure that we're advocating, this is the tree that we're synthesizing. This is the tree that's telling us in each branch what is exactly the probability and what is the level of demand of the two different chemicals. And we do that over multiple stages. And notice that actually here, this nonlinear programming problem, which we solve with IPOP, is only of the order of 12 seconds. So it's actually, quite efficient to generate this. Again, not too surprisingly, we can predict a better profit with the approach that we're proposing versus using the heuristic. But it's not only that, it's also the type of solution that you get. Here, for example, I want to call to your attention, look at the levels of inventory. Blue is one of the heuristic, so this intuitive tree. The other one is the matching one. And you can see, for example, at time period 1, we're way overestimating the inventory that you would require for this product D. So you're also getting not only different objective function value, but also potentially very different value for your variables. Okay? So with this, I think I've reached the end of my talk, hopefully within the required time limit. So I hope what I've shown here, that we can avoid being overly conservative in robust optimization using the idea of recourse. We saw that with cryogenic energy storage. We also saw that we can solve effectively, two-stage, multi-stage optimization problems, but it's not straightforward. You need to do a lot of things like tightening relaxations and so forth. We saw that with the supply chain. We also saw the area of endogenous uncertainties, which again, I would call to your attention. This is really an area where there's very little publication, very little work, and I hope there's more interest in that. And oil field planning is a great application for that. And lastly, I think, which is also a very important point, we need to make sure that the qualitative information that goes in those models is good in the first place, and that's making use of that historical information. Now, obviously, there's lots of open problems, lots of open questions, just to mention two of them. Of course, going to the nonlinear version, that's a big step. Everything I've done here is mixed integer linear. There's been also very little work on that end. And the other one, which is also very important, these models are not very straightforward. So how can we make users understand what the answers mean? That's actually, I think, also a very important problem. And here, finally, I'd just like to acknowledge, support from NSF, the Goalie program that we have with Praxair, Fulbright program that supported Pablo, and then also support from Dow and ExxonMobil. So with this, I'd like to thank very much your attention. I'd be happy to answer any questions. Thank you.
Thank you very much, Ignacio, for this presentation and opening lecture. There is no uncertainty, however, about the time of our coffee break, so we have to, we were going to have a 40-minute break in almost 8.5 minutes. So we will take a few questions. Please name your, identify yourself and wait for the microphone. So here is one. Professor J. Lee.
Yeah, Jay Lee from KAIST. Enjoyed your comprehensive talk very much. You brought up this issue of endogenous versus exogenous uncertainty.
Right.
And also going to problems with multi-stages, with many stages, scenarios are going to be exploding.
Right.
Now, I'm from the control community.
Right.
We face this problem all the time, right? With most uncertainties in control are endogenous uncertainties. And we usually solve very huge multi-stage problems, even infinite horizon problems. And the way we dealt with, I'm not saying that we have been successful in getting the answer, but the way we have been approaching this is very different from what you've been talking about. That we are used to state-space formulation, so something that's equivalent would be Markov decision process type. Right. And then the tool that would come up is dynamic programming. Right. And of course, you have the curse of dimensionality, so you go with approximate dynamic programming. Some of those work wonderfully for inventory type problems and so on and so on. Have you looked at any of those approaches, and what is your perspective in terms of using some of those control oriented approaches in these types of problems?
I think specifically, and you have a good point. Obviously, I did not cover here all the approaches. I missed, for example, also the fuzzy programming and so forth. There's a whole set of other approaches. Now, the thing with approximate dynamic programming that I would say is kind of an issue, at least for many of these problems, is the part of the model. Because usually to effectively apply, and probably know that better than I do, when you do dynamic programming, you need to discretize somehow the space. And that's where the difficulties usually come in when you have equations that involve things like mass balances and so forth. It's not always trivial to see how you do that type of discretization. We actually do have at Carnegie Mellon a colleague of mine Nicola Secomandi in the business school. He's very much an advocate of approximate dynamic programming, and we have these type of discussions. So keep in mind, I do have to admit, the approach that I've presented here is very much based more on what I call math programming, where the starting point is really the model itself. And in that sense, it tends to be, a more, if you wish, intuitive approach. But having said that, obviously, there are applications. I remember one application that had to do with design of elevators in a building where actually approximate dynamic programming was the way to go. But the reason it was very successful is because we could actually discretize basically the state. That was pretty much it. And that's, I would say, a complication that at least at first sight is not so trivial to overcome. Okay? Yeah. Right.
Any other questions to Professor Grossman? Anna.
Okay.
Ana Barbosa Pobo from Lisbon University. Thank you very much, Ignacio. It was a very nice talk, as usual. My question is related with robust versus stochastic programming.
Right.
What really do you advise us to do? Because we have been doing a lot of work in stochastic, and the application of the robust is still quite fuzzy. So what you really recommend?
Yeah. Well, again, I mean, it's very difficult to have sort of a clear-cut answer to your question, but as a first approximation, I would say if you have problems that tend to be short-term, usually robust, and I thought that actually when Jay was going to ask me the question that he would brought up the idea of robust, control, because that's where it makes sense, because actually that's the other issue. When you do short-term, recourse is basically not even an option that you might be able, for example, to implement. Now, if you look at long-term, let's say like the oil field type of problem, we're talking 5, 10, 20 years, I would say robust optimization is not appropriate in general because of the key role, first of all, that recourse plays, but secondly also because of the multi-stage nature. Now, having said that, we also have to realize, as I presented here, there is increasingly the idea of at least doing some recourse in robust optimization. So part of that may be overcome. But by and large, I would say short-term is robust, long-term stochastic programming.
Okay, I think this is a good moment to stop. Let's first thank again Professor Ignacio Grossman. Ignacio, as a token of our appreciation, would like to thank you for your opening plenary lecture.
Okay, thank you very much. Thank you. Thank you.
And there is going to be a small announcement. Yes. Thank you.
Yeah.
Sorry, thank you guys for all coming, staying one more minute. Just about the logistics for today. If you have any questions about anything, don't forget to look in the program or the app. Most of your questions should be answered, otherwise come find organizers. Hopefully we can help you. There's a break downstairs in Hall A, so you go down the stairs and straight through the doors, and there's a coffee break until 10:30. The lunch will also be in Hall A and just downstairs in the foyer where the reception was last night. And then tonight for the reception at the town hall, there will be taxis and you can take the metro, etc. to the town hall. Just don't forget to bring your ticket. They won't let you in without the ticket you got when you went to the registration desk. So that's it. Thank you and enjoy the coffee break.